Okay, so welcome back to our course in cyber-physical systems, and we are going through chapter 4. On the first three topics of the chapter, we're going to be covering an introduction to the Internet of Things, RFID technology, and wireless sensor networks. And today, hopefully we can finish that introduction to the Internet of Things and move on and hopefully also cover all of the RFID technology part. So just to remind some of the points that we were discussing last time, the availability of the Internet and advances in communication in general have led to this opportunity of conceiving this Internet of Things paradigm where everything can be connected with each other in the network. So the idea is that we'll be able to see and identify any type of entity on the network, and the ability of these things to be able to gather information, transmit data, and gather data from the network will make these devices smarter. And also, if you have these devices that have the ability to gather data and process it, now you have this pervasive computing platform that is distributed in nature, but you have access to a lot of computing. So the idea and the challenge actually is, how do you make use of it? What are the distributed processing algorithms that need to be generated and developed to take advantage of such a paradigm? Because when you start connecting all these entities, you can see that at a minimum, you can have 4 different and distinct ways of communicating. You can have person to person via the things that they have and that are attached to the network, to the Internet of Things. You can have person to machine, sometimes with the fact that we have here person to machine and machine to person implies some types of server client architecture. So if we are talking peer to peer, then person to machine or machine to person really doesn't they're not different from each other. But if you have a client server architecture, then it does matter, because one is the client and the other one is the server. So we have to be mindful that we can have peer-to-peer type communication from a person to a machine perspective and from a machine to a machine, or we can have client-server communication structures between a person and a machine. So that just emphasizes the pervasiveness of the computing platform, the communication, and the network. When you think about all the people that are connected to the network and all the things that they have that can be connected to the network as well. If you go back and think about technology, how technology classically has advanced the state of progress of mankind, 4 examples here. How the wheel, for example, became an extension of the foot, so something more primitive. Or clothing has become the extension of the skin, so we're protected from the elements. And we're very comfortable how computers have become an extension. And please, I emphasize the word extension, so we're not talking about replacement. It's an extension, it's a complement that makes things better. So that's a key distinction. So we are very comfortable with computers being an extension of human intelligence. It helps us do things faster. It helps us sort through patterns that otherwise would be very difficult for a human to undertake and do things easier. Well, the Internet of Things can be seen as being an extension of the fabric, this network of humans that we call society, because now we're bringing all these data and we're bringing all these objects to coexist with us. So think about the possibilities there. They can be actuating any type of and exercising any type of control, making decisions autonomously. They could be identifying other things, events, data, and sensing everything that is around their environment. So this is really the essence that enable pervasive computing, which we have a chapter on, and pervasive network connectivity. So that's the point, that everything is connected to everything else in ways that we perhaps have not been able to think about or materialize before. When you have this type of disruptive technology coming about, what it does, it also becomes a catalyst for new technology. So that allows people to think of even other things that are even greater. So who knows what the next generation type of networks may look like. We're going to go through a few architectures and a few topologies later on in the chapter, but who knows what could be construed or what could be architected with this type of connectivity and distribution of computing power. And at some point, no later than at the end of the RFID part, I'm going to give you a tangible example, and hopefully you guys will find interesting, of an actual product that I'm involved with that really touches on all these aspects of RFID, Internet of Things connectivity, and so on. So the enabling technologies for Internet of Things are RFID. So that's an important one because we do believe that being able to identify things and extract data that they may contain, as we will see, is an important and an enabling technology for the Internet of Things. Then technology on smarter sensors and actuators. Part of being smarter is being able to use it in an easier way. And we know that if these things are distributed and they're small, low power consumption is implicit in one of the needs of the Internet of Things paradigm. So part of making sensors smarter are to make them less power so that they consume less power. And being able to understand, for example, that we are not talking just about the power caused by the actual activity of the device, but we have to care also about the power. We have to care about the power that is quiescent in the device, meaning that it's not dependent on activity, that is just there constantly due to the leakage of the electronic components. So every part, every contribution to low power needs to be looked at and minimized, and people need to understand the sources of power draw and distribution. So that's another enabling technology, better sensors and actuators. And then, as we discussed in the last chapter, making things smaller. You'll see that these RFID chips are really small, and the size that determines the label of the tag is really the antenna, which is a function of the area that you want to cover. So if you don't need to cover a long area, so then you can also scale back on the antenna. So making things smaller, we talked about MEMS and NEMS, so nano electromechanical devices. So nanotechnology and bridging the gap to being able to connect to the body from a molecular perspective. There are sensors and actuators that are being grafted into people's brain tissue to be able to send signals as well as to actuate or prevent. For example, we are starting to learn that if you apply a specific stimuli to the brain, maybe you can prevent people from having seizures. That's important. And now, if you attach a sensor and you attach a transmitter to that device, then that person could be monitored. So a lot of opportunities. And this overall, these processors being so low cost and having enough memory and processing power to do some type of intelligent processing become these smart entities. Because now software can be done not just on big computing elements, but everywhere. So that's the affordability of these devices that is making this Internet of Things paradigm possible. RFID and sensor, so that's another technology. And once you have these processors with the ability to connect, they can communicate with each other. So people, what they have to do is come up with the application. If anything, what can slow down the coming about of this technology is just the lack of applications and people thinking about it. And the people that are more prone to think of things are not even engineers. So I like to stay in contact with entrepreneurs and people that are not even engineers, because I hear a lot of good ideas and they have no clue how to do it, but they say, wouldn't it be cool if? And what comes after, then it's up to an engineer to actually make it possible, knowing the technology and how to use it and deploy it. So that's a very fun relationship with someone that is kind of like a child that doesn't know the boundaries and tells you, I want to do this, and then they're not limited by our own I think technical prejudices of we know too much about the technology, so we think that things cannot be done. But once someone tells us, wouldn't it be possible or wouldn't it be cool if, then we kind of change our mindset and say, well, yeah, actually it could be done. And then we can actually apply our knowledge of technology and engineering to do it. That is a very productive and symbiotic relationship, entrepreneurs and engineers. Sometimes they are both, the same person. But I see a lot more entrepreneurs that are not engineers that are more successful than the engineers, even though the engineers are the ones that make it happen. And as part of that effort and that team, they are successful in their own right. So when we have this power, some of the things that we'll be able to do. Automation everywhere to the extent that we want, supporting various activities around our lives, around our human lives. So connectivity to build a smarter world overall. So this refers to not only the benefit to the individual, there will be benefit for the individual, but also a collective benefit as well. So those are two different things. There will be applications that will have a collective benefit, and there will be others that will be more targeted to the individual. There will be applications to make it easier, more effective, more cost-effective to protect the environment. That's important. Our homes. We talked about manufacturing industries, how they would be affected. We talked about that in the last chapter. And all in all, our livelihood, our offices, our safety and security. We talked about smarter infrastructures. Transportation and logistics with RFID, the ability to keep and sense the state of goods that are being freighted. So if you are tracking a cargo of bananas, are they being stored at the right temperature? So that, we have heard cases of salmonella or some other actually wreaking havoc for some food chains. Well, I don't think that happens because people want, but these problems are real, and they could be eradicated with better technology, keeping track of shipping of goods and sensing the environment around them, meat that is being stored at the right temperature, things like that. So there are many applications for this type of technology, embedding these services and communication devices all over the place. So when you start getting this multiplication effect in the connectivity, you really, the point is, it's not really a hype or, some science fiction idea. These are things that a lot of people feel passionate about, and they want to advance the state of the art of the technology. So, actually, I'm working on. So the project I'm working on is actually two parts, but I'll leave that for later. But because I just remembered that it had two parts. That one is technology development, the other one is the application of the technology to an actual product. But I really feel very passionate about the opportunities that Internet of Things is bringing to us. So the best way to do that is to help people realize their product. What's happening is that we were just getting comfortable with, now we're going to have information, communication, and communication technology that can give us connectivity anytime, any place, for anyone. And now we're going to be transitioning to connectivity for anything. For anything, at any time, at any place. So that's another dimension. That's what the Internet of Things paradigm is bringing on. So back in 2005, and these are, a body consisting mainly of diplomats, but the UN issued a report that we would have billions of entities connected to the internet where humans would be a minority. Okay, so that was the vision. And if you look at the chart, what are the things that have happened, what technology reach have taken place since the beginning of the century? RFID is something that emerged early on. And again, I keep saying this, it hasn't been deployed enough. Because, again, you have to find the right applications, but it will be. So RFID, and we have seen cost reduction on services and products for surveillance and security, healthcare. We looked a lot at this type of applications in the last chapter. And then going beyond, like from now through the next decade, what we're going to be seeing is the ability to really connect things that are far away, to really reach via this connectivity things that are not next to us, that are far away, for tracking, for collecting data, and so on. So at this point, if you have all this data, another term that has come after the Internet of Things, but you surely have heard it, is big data, and the ability to look at and try to discern patterns patterns from huge amounts of data. There are terabytes, and some visionary companies, for example, Google has an effort where they collect all types of data and they just dump it into these terabytes, daily terabytes of data. And they actually are looking for ideas how to use the data. They give you the data. They want people to come up, because connecting things and collecting the data is sort of, from a technology perspective, is the easy part. Although there are obvious challenges, but it's more tenable. The thing is, what do you do with it? So Google has all this data that they collect on all kinds of things. And they're looking for people to being able to parse it, segment it, extract it, and convert that data to some type of information. So it is when you transcend from data to information that you have something useful that you can do something with. So, so big data, that's another dimension on the software side and algorithm development side, how to come up with the algorithms to be able to just access the data. The amounts are large, so algorithms to just access it, so it doesn't take forever to get to any specific piece of the data. That there are people working on that. That's an area of interest. And once you do that, how do you, now that you can get to it, how do you extract the one that is relevant? How do you find those patterns? And how do you eventually convert the data into information? So it really can form, once you start looking at data of things and people, and the data that comes from the interaction of those, is all kinds of new opportunities arise from that. So at this point, I'm going to show another short sort of, I'm going to show another short YouTube video like the one that we looked at yesterday. And this is the last one, but this too I found appropriate. So
over the past century, but accelerating over the past couple of decades, we've seen the emergence of a kind of global data field. The planet itself, natural systems, human systems, physical objects have always generated an enormous amount of data, but we didn't used to be able to hear it, to see it, to capture it. Now we can, because all of this stuff is now instrumented, and it's all interconnected, so we can actually have access to it. So, in effect, the planet has grown a central nervous system.
So there's about 1 billion people using the internet at the moment, and that's set to grow to probably 2 billion in the next couple of years. And we think that's quite a lot, but over the last 10 years I've been looking at devices being linked up together using networks, so little sensors on things, these temperature sensors and traffic sensors and flow rate of water and how much electricity, all transmitting data. It won't be long, and it may even have happened already, that there's more things on the internet than there are people on the internet. That's really what we mean by the Internet of Things. Then you get this sea of data that you just drown in, literally. And there's this triangle that's been quite well documented called the DIKW triangle. That's data, information, knowledge, and the tip at the top is wisdom. The D at the bottom is a sea of data, and when we get this data back home and start doing stuff with it, we apply intelligence to it and transform up that stack. So we go from data into information, information into knowledge, and then glean some wisdom from that. And that's really what the analytics part of our Smarter Planet story is all about. But the ideal day, I guess, would be that I wake up in the morning and my alarm clock went off at the right time because it had looked in my diary to know when my first meeting was and had backtracked which ferry I need to get and therefore what time I need to get up. The bathroom heater would have been on for half an hour before that time to make the bathroom nice and warm. I'd know that the temperature had been freezing overnight and therefore that my ice was going to need to be scraped off my car, so I need to leave the house 5 minutes earlier. And then I'd be getting a notification, perhaps an audio announcement in my car as I drive to the ferry saying, oh, the ferries are running 5 minutes late, so no need to rush, just take your time. All that stuff is being handled by autonomic systems of little agents looking out on my behalf for the things it knows I want to do, just making me aware of what's going on so that I can plan my day accordingly. So the system of systems is really what emerges when you start to link these things up. So the fact that you've got isolated systems, for example, my house on its own, with its energy monitoring and the water monitoring and the detecting if the windows and doors are open, that kind of stuff. It's a system, certainly, but it's not a system of systems. But if you start to think about the power grid, first of all, the appliances negotiate with each other. So they say, okay, guys, Andy wants all three of us to operate, but it's going to be bad for the grid if we all go on at the same time. So now suddenly we've got systems talking to each other, sort of acting smarter because they know about each other, which overall makes the entire system more efficient.
There are more human beings living in cities now, as of last year, than ever before in human history, and that doesn't look like a trend that's reversing. For every 4 text messages that a pedestrian sends while walking down the sidewalk she's on is sending an equivalent amount of data. There are sensors all over the place, certainly in the water main. They're registering blockages or not right beneath your feet. Taxis are, broadcasting their position and fare status back to dispatch. Trains and buses are updating their locations in real time, which people are reading on that street corner. A matrixing of services creates a more resilient thing. And, we can let a water main blockage speak to the road signals above it and do something quickly before police can get there. Soon enough, we will just expect to be told exactly when the bus will arrive.
Look at that complex set of relationships among all these complex systems. If we can actually begin to see the patterns in the data, then we have a much better chance of actually getting our arms around this. That's where societies become more efficient. That's where more innovation is sparked. When we talk about a smarter planet, you could say that it has 2 dimensions. One is to be more efficient, be less destructive, connect different aspects of life which do affect each other in more conscious and deliberate and intelligent ways. But the other is also to generate fundamentally new insights, new activity, new forms of social relations. So you could look at the planet as an information creation and transmission system. And the universe was hearing its information, but we weren't. But increasingly now we can. Early days, baby steps days, but we can actually begin to hear the planet talking to us.
All right, so that's a very smartly done video, and kind of highlight some of the things that we've been talking about. So it's a nice way to kind of summarize and end up the part of the chapter on an introduction to the Internet of Things, and then switch gears to RFID technology and go through that. So RFID is a technology that allows you to identify something via a tag. So it has this specific part of the overall system, which is a tag. Its main purpose is to identify. So you have a serial number on this RFID tag. And when this tag is queried, it sends its ID. So the tag has an ID, unique ID, and when it gets queried by another part of the system, which we're going to be calling the reader, it sends this ID. And we'll see the tag is a transmitter, is a receiver, and is also a memory. Those are the three main components. And of course, to manage all that, you have to have some type of processor in there. So the different ways of and the different reach of this information that is in the tags varies depending on the standard, depending on the frequency, and so on. But these chips that contain the memory, the processor, and the transmitter and the receiver, all integrated on the same chip, you can attach it to some type of, or first you can encase it on some type of casing. It could be disc, but you have seen your toll tag transponder, so that's one type of casing. But perhaps the most fascinating one is on a label, on a paper label. You can put it on, glue it on paper. And then the metallization for the antenna, you can basically have paper that is covered by metal and etch away what you don't want, and what you are left with is the antenna that you do want. And then we'll see that there are two types of RFIDs. There are active and passive. Passive means that you don't have a power source within the tag. So it's all powerless, dead circuit, okay? And then, of course, the active is the one that has some type of power source, namely a battery. So why wouldn't you want to have a battery? Well, battery has a finite lifetime. And if you want to have something where you're going to stick on something and behave and get the same utility that you would get from, let's say, a barcode, which is just there, or some type of text label that is there, and you always will have that information there, except that with the barcode reader, you have to get close to it. And if you have some text, you actually have to look at it and read it. If you want to have that same type of utility forever, then you don't want to have to rely on a battery. So these amazing things, they are dead circuit, but they have technology for another part of this is energy harvesting. So another thing that you have in this label as part of the metallization that you put together is a capacitor. So that you can actually harvest energy from the same reader that is trying to query you, and then charge up that capacitor first, and then use that energy that you harvested from the same RF frequency that you're going to be using to communicate to do the rest of the transaction. Okay? Receive the command and then send your ID. So that's sort of the way it works at a high level. So if you look at the part of the system, so here you have some type of antenna, and again, if you have a passive system, you have a capacitor, and then you have the chip. The chip has a controller, a transmitter, RF transmitter, and an RF receiver. And what you get from the reader on the other side, which is normally attached to some type of host computer that runs the whole application, you get first energy, you get timing, so the transaction can be controlled, or timing and command, and then you get data back and forth. You can basically communicate with this with RFID tags. So again, from the perspective of the tags, the most widely used ones are the passive ones. They're used for inventory control, and another big usage of them is actually library books, for library books. So these are very low-cost paper paper tags. If they have a battery, then they are active. And then there are some hybrid type systems that people have conceived and not really use a lot. For example, you would power this is to extend the battery life, okay? And whether they get called semi-passive or semi-active doesn't really mean a whole lot, but the whole idea is that you try to power some part and not the other one. So you would power the processor part, but then the RF front end, you would leave it to be powered from energy harvesting, and you would save battery life that way. So there are some hybrid systems, but mainly you have the passive and the ones that are active, which have a battery, and those have their own characteristics. We also have different frequency bands that they operate at, and we'll see that as well. So if you look at the architecture of the physical architecture of these things, you would see that they have the chip, and then they have some type of coil-like antenna that lends itself to energy harvesting, because with a coil you get some inductive-like coupling through a magnetic field, or to the magnetic field part of the electromagnetic radio wave that you are receiving. Okay, so remember that an RF wave is an electromagnetic wave. The electric part of that wave, the electric field part of that wave, doesn't help us at all in energy harvesting. Is the magnetic part, because with the magnetic field we can induce a current that helps us charge that capacitor, and we can use that charge as energy. So that's the fundamentals physics of it. Now, from a communication perspective, the electric field is important for the communication part. Normally, if you are very close, then communicating through just a coupled magnetic field is sufficient. Okay? But magnetic fields by itself don't travel far enough. You need the E field part. And that's where we communicate with electromagnetic waves. So if you're very close, inductive coupling via magnetic field, sort of like a transformer type coupling, or basically two inductors where you have on one side running a current that generates a magnetic field. That magnetic field couples into an adjacent inductive coil like the one depicted here, and then that magnetic field induces a current on that side, and then you can use that current for energy as well as communication. Only works for communication. It only works on the when the distance is very short. But once you have, a few inches away, you need the electromagnetic field, using the magnetic for energy harvesting, and then using the electromagnetic wave for communication, just as any radio type of communication. So this is actually a picture here. Some tags, they use both a coil for inductive coupling of energy, and then they use a dipole type antenna for the actual data communication. So you can see here, in this one, this black part here is the actual chip. That is about 3 millimeters by 3 by 2 millimeters. That has a processor, that has memory, that has an RF receiver, and it has an RF transmitter. All that is in there. This big coil here, that's the inductive loops to do energy harvesting. Here we can see an antenna structure for communicating from an RF perspective. And these structures here can be a capacitor. It could be a capacitor, a power source that is coupled via the coil as well. So that's an actual construction of an RFID tag, and all these other structures here, those are to give them some mechanical strength, because it seems that this one is not a flexible one. So if you don't want it to be flexible, you have to stiffen it with some type of mechanical structure. And if you are deploying patterns of metallization on some type of paper, you can do other patterns as well that serve as mechanical structure. But all this you can put on paper or on some thin plastic or some a small casing. The only thing that, and if you're using paper, you can actually print it. So you can print a mixture of copper silver alloy that is not as is more durable than plain copper. So you can print that material on paper, and then this the chip, you just glue it on with some strong epoxy-based adhesive. So it's as simple as that. So what are the specifics of a passive tag? Again, these are the most widely used. Why? Because you don't need a power source. We don't want to have to, well, if we're talking about millions and billions of things being identified and putting this thing on everything, that's a lot of batteries to replace. So that's not really feasible. So it's now, it shouldn't be a surprise that the most applicability has been found in the passive type of transponders. So these are the ones that when the reader part is constantly broadcasting a signal, that when it matches the signal that the RFID coil is tuned to, that excites that coil, and the RFID comes up, it charges the capacitor, does the energy harvesting, stabilizes the power, its power source, and then turns on the receiver and listens for the RF part of the transmission. Am I being queried? And towards the end of the section, all this is governed by standards. So imagine if everybody was doing their own thing. There are a number of standards governed by the International Standards Organization, and there are standards for each specific protocol, for each specific frequency band. So this is being done in concert worldwide by technologists, so people can come up with products and they work with each other. So remember, the interoperability aspects of good systems engineering that we discuss, or we've been discussing since the beginning of the course, is not being lost. And you can see hopefully how it is actually a must to get all these technologies talking to each other. So when you get, if you are in a specific frequency band and you are following certain standard, you will get a specific message that has a specific format. And maybe that message is saying, identify yourself. So the processor, after that RF signal is demodulated and converted into digital data, the processor parses that command, it knows what the ID is, and then it turns on the transmitter and sends his ID. The reader basically grabs it off the RF signal, decodes it, and now it has the ID. Now all that happens in very few milliseconds. Okay? Looks like a lot of activity, but it all happens in milliseconds. The only thing that you have to worry about is, okay, what is the distance? And that is a key thing to utilize this technology, that you have to be very mindful of what distance does your application require. And it varies widely by antenna size, the strength that you put also on the reader, which you have that ability. The reader is powered. What you don't want to power is the tag. So, but you also have to know that the tag has to get back to you, and it only has so much power that it can harvest. So there are those issues, and they are governed by the standards as well. There are different standards for different applications, and that's great that that's happened. And at the end, there is a chart with all the standards that I'm going to leave for you or with you in this presentation, which eventually will be available to you on Canvas. So if you are a RFID, you have 96 bits of memory. Not a lot. We're not talking about a lot, but 96 is a lot of bits if you know how to encode different parts of the information. So you can have, for example, a header, some type of EPC, which the standard borrowed from the standards for the barcode. So the electronic price code, that's what EPC stands for. So, because that's the application that it was meant for, or the main application that it was envisioned, was how do we make something that can replace the barcode, but that you don't have to get close to it. That's the idea. That's the utility value. And then you can have, you can classify the object, and you can have 36 bits of a serial number. So these things are very inexpensive, very, very inexpensive, because in electronics, is probably, in semiconductor manufacturing, is probably one industry where economies of scale apply very, very well. If you have volume behind an electronic product, you can drive that price down very effectively. One, because the manufacturing is planar, so you can just make the wafer bigger, and you get a lot of more processing of parts doing the same steps. Doesn't cost you any more. But the other thing is, at the end of the day, the raw material is sand. So we have a lot of it. So there is no lack of raw material. So it's just the effort on the investment, the capital expenditure, to come up with very, very expensive and sophisticated equipment to process sand into these circuits. But if you have the volume behind it, then it spreads over that volume very effectively. From a financial perspective, it spreads out very, very efficiently, economically. So these things are really inexpensive. We're talking about, if you're buying them in thousands, I think you can pay like 2 cents for it. And you're getting an antenna, a transceiver, a chip, and a memory. So the other type of the transponder, the tag, is the active one, the one that has a battery. And really, that's the only difference. That's the only difference, that it has a battery. Now, what you'll find is that the passive tags, they cover only the lower frequency bands, because to switch and to oscillate at a higher frequency requires requires more power. Now, there is a ton of benefit to operating at a higher frequency, like 2.4 gigahertz and beyond, into the microwave range. There is a lot of benefit. And except for some narrow frequency bands, with higher frequency, it's easier to transmit through objects and walls and get further transmission. So there is a lot of benefit. But it requires more power. So you will see that active tags, or you will see that tags that cover the higher frequency in the gigahertz part of the spectrum are normally active. They have a battery, and they can cover higher distances because they can radiate more effectively with more power. That doesn't mean that you cannot do active on the lower frequency bands. You can do that as well if the application, if it makes sense for the application. But what you will find is that all the passive ones in the lower are in the lower frequency band, and that's less than 1 gigahertz. But we'll go through the frequency dichotomy later on, just giving you the background of the passive versus active. But other than that, the operation is pretty much the same. Now, the other dimension of these tags is the memory organization and configuration and technology that they use. So in there, you have tags that are already come pre-serialized. They come pre-serialized, and you basically it's a unique identifier. You're buying a unique identifier that cannot be changed, but is guaranteed by standards and manufacturers that is unique. And all you can do is slap it on something and read, and then you know that that is the ID on that object, and you can know its location that way through some reader gateway. So there is certainly a usage for that. Then the other one is what we would call write once and read many. So that is a type of memory that you write it once and then it becomes a read-only memory. Normally the way that you write these memories is some type of platform, and then you deploy it to the object where that you want to identify. And you have some access to the chip, and the way to program something once, and then you can read it as a regular memory is by essentially it has tiny fuses, and you blow the fuses, and the way you blow them is either a 0 or a 1, and then you have programmed it forever because you physically changed the structure of the material. You cannot reverse that. So, but certainly less expensive, and there may be applications for that. For example, if you have some type of payment card, like a credit card, that is going to the manufacturer, Visa just have these blank cards. They don't know what number they're going to be assigning, and the name, and they program in this card the number and the name of the user, and then they mail it to you. So that's an application where you want to be able to write once in the field. There is no need to be able to write again because that card is not going to be reused by anybody else. That's an application that would warrant the ability to write once in the field and then read many times. Then you have the one that you can read and write multiple times, and that has memory technology that is essentially flash memory, or double EEPROM, which is electrically erasable read-only memory, but flash is more common. And if you don't know how flash works, basically it has a special transistor structure where you get charge trapped into a double gate MOSFET. So without power, the charge gets trapped in this floating gate, and you keep the charge, which programs it to a 0 or a 1. So because it has to remember that this tags can be on power, so it has to be there. When you program it, well, you can program it many times or only once. It has to be non-volatile. Non-volatile meaning that the programming of the memory or the data in the memory will persist without a power source. So those are the three types of memories that these chips can have. So that's another dimension of RFID technology. Then there is the frequency band. So in the frequency band, we have low frequency, which is 30 to 300 kilohertz. So low frequency doesn't travel very well. So at the low frequency end of the spectrum, actually, because the wave behaves mostly magnetic, so it doesn't travel very well. So at the low end of the spectrum, the application is what is called near field communications. So all your phones already come with a reader. So a near field communication reader. So you can use your phone. If you get the NFC, near field communication tools, if you have it, if not, you can download it from the App Store. You can read IDs already, but you have to get really close. You have to get like next to it like this. It's about 2 millimeters in range. The application of this is payment systems. And frankly, for a payment system, I want to be close to the payment terminal. I don't want to be broadcasting my payment ID. So it works. NFC, Apple Pay is the most widely used system. But this already has it in here. And I don't know, this is a pretty new phone. I just got this weekend, the Galaxy S10. And it also has inductive charging, which is a way to, through magnetic couple energy and charge the phone. I don't know how they did it, but you could combine and use the same coil for NFC and inductive charging. So up to the designers of up to Samsung, right? But that's the application of this low frequency. For the tags that we have been, and the application that we have been discussing, the other ranges are more usable. First, the high frequency, which is 3 to 30 megahertz, namely about 13 megahertz because you want to operate in what is called the ISM band, which is kind of a scientific band that the FCC, at least in the US, have left for certain applications, and that's around 13 megahertz. So that's the frequency that most high frequency band tags are using. And at that frequency, you find a lot of the paper tags that libraries are using are operating in that frequency range, and you can get about a couple of feet in range very effectively, depending on the antenna, of course, depending on the antenna of the reader, which helps with transmitting power and helps with sensing whatever is coming back if it's too weak. Normally, it works very well at about 10 centimeters. So remember, the low frequency, near field, couple of millimeters, less than 1 centimeter for sure. The other one, you can have very compact, very nice systems and operate very reliably at 10 centimeters. So scanning books and things like that, very effective. Then there is the ultra high frequency, which normally operates about, there are two bands, about 400 megahertz, but the most widely used is really about 900 megahertz, which is the same band used by the older cordless phones that nobody has anymore. Okay? I don't know if you remember, but there were phones using 900 megahertz. It's the same band. And you can get several feet on that band. That is used a lot for retail price tagging and things like that, where applications where you can stand a few feet away from something and read the contents of the ID. And then again, depending on the antenna, all the way to like 30 feet, you can get ranges like that on the ultra high frequency band. Most of the tags in the high frequency and ultra high frequency are passive. That's the sweet spot for passive tags. Near field, they can be passive as well, but again, the application is a little bit different, targeted more at payment systems. So, in a sense, the credit card can be a passive near field communication type of tag, for example. And then you have the microwave band starting at about 2.4 gigahertz, which is the same where Bluetooth starts in the Wi-Fi. So those are active. You require a power source to transmit on that band, but you can have a lot of range. And if you use a network with repeaters and things like that, then you can really cover a vast area. So, think of a shipyard with containers, and where is my stuff? If you are into a business of freight and things like that, you can actually track and identify freight that way and cover really many meters. So those are the bands for RFID tag technology. So then, just to kind of summarize, we have the components, processor, memory, on the tag, energy harvesting system, including a relatively big capacitor to store the charge and make the transaction possible. Then we have the reader. We have the reader, which sends energy in the form of RF, and after that it makes the query and it gets data. It can also send data. If you have a memory that is writable, part of one of the commands in the standard is write this data to some memory location, just like a memory write transaction. So the reader does that, and then it communicates with some type of host computer that takes care of everything else from an application perspective. So here's some tags. A lot of them come in key ring type fobs. So those are for access control. So they are useful for access control to cars as well as to domiciles. So that's an application of the fob form factor. You have it in payment system, so you can see sort of a credit card there. Another application is in access control of the card form factor that you can read and write, because you need to, is hotel room keys. Because the magnetic strip is really unreliable. And it's not durable at all. It wears out very quickly. So access control of hotels room with RFID use the card factor, form factor, and it uses the memory where you can read and write, because a particular card can be assigned to different room at any time. Then you have the smart label. So that's the one that is used for retail as well as library book control. And then you have different types of discs that you can use also for apparel, inventory control and pricing. And from first-hand experience, I know that, for example, these discs are very, from an environmental perspective, the discs are tough. They're basically plastic molding completely solidly the circuitry and the antenna and the coil. So you can throw it against the wall, they don't break. It's compact, it's molded. So basically you poured molten plastic around the overall electronic structure, and now it's compact. So you can throw it because there's no vibration. There is no free space to allow for vibration. So it doesn't break. So discs like this, mainly when they are, when you use a plastic compound that is resistant to corrosion and things like that, they can be used to, for example, I know from first-hand experience that industrial laundry businesses that do the laundry for hotels, or even hotels that have their own big laundry places, a way to control the inventory is by tossing some of these things on the washer with the laundry load. So if you have a business and you're doing laundry for hotels, then you want to know a good way to keep track of which hotel is this load, is to throw these discs in with the clothes, with the linen, basically, okay? So that's an application, and they're tough, okay? Another application is this other form factor, which is a glass housing, which can be used to identify pets. So this is something that gets put in pets to identify them. And my cat has one, so they work. And so that's another form factor for the RFID. So you have different form factors, you have different frequencies, you have different memories, and then you have, one part of the design of the system is to understand very well what is the size, the range of your application, so the antenna design is important. Because you don't want to overshoot the range either, because then if you have multiple readers and you want to associate some tags in the vicinity of this reader, if you overshoot your range, then maybe the other reader gets confused. So that's a system level care about that you need to take into account depending on your application. So these are more on the tag form factors. So I'll just go through that. And then this is another schematic of a label type RFID. So you can see here the capacitor. This big structure here is a capacitor. So the capacitor is, you can see where you cannot integrate the capacitor. It's a big structure. And physically, you know that how much charge you can store depends on the size of the capacitor, the physical size. So that is a constraint. How much energy you need to make it, to do a transaction, and then you can easily calculate how much charge you need to store, and you can easily calculate how big the capacitor needs to be. A simple parallel plate capacitor with rectangular plates. But again, you can print a lot of these structures on plastic or paper with some type of copper silver alloy. And you can print it with very, very fine resolution. I mean, it's really the same technology as inkjet, but instead of having ink, you have basically a solution of copper silver that you keep warm and or molten, and then when you deposit it, it hardens. It cools and it hardens, and then you have something that you have printed. Or the other way is etching. So essentially etching is you have everything covered by metal, and you put some type of, then you cover it with photoresist, and it's sort of like a photographic, all photographic development process where you shine some type of light, and that changes the chemistry of the photoresist, and then you wash it off, and the other one that was covered, that didn't get the light, that stays there. But then you put the metal with the absent photoresist in acid, and everything that is not covered by the photoresist goes away, and then you get these metal patterns on the label. Very similar to what is done for chip processing, same thing. So this is a summary of the systems. So you have tags, you have antennas on the reader, antennas and the reader, and then you have the host computer. And to summarize, the tag stores information, relays the information, receives information and stores it if it's a read memory, and manages the energy or harvests the energy to make the transaction possible. You have different antennas. That's a key part to match the range of your application. Then you have the reader, which goes through the standard protocol of sending energy for the energy harvesting, and then at that point managing the tag, either telling it to store information or give information or both. And then the reader passes that information to some type of host computer. Okay, and that host computer does whatever it wants with it, depending on the application. So this is just another same idea for the previous one was for passive, more for passive systems. This is for active. So obviously the only difference is that for active systems, you don't have to send the energy harvesting preamble of the packet. You don't have to send that part because the tag has its own energy source, but everything else is the same. And normally what you see is that with active systems, they can afford to be bulkier, and so they can afford to be bulkier because they don't consume more power. And finally, this is a chart with all the standards. So everything that is in this column are all the applicable standards for different frequency ranges. So you can see that the standards body, ISO, the International Standards Organization, they have been developed a lot of standards to make sure that there is an interoperability of the technology. It's a little bit fussy, but this will be in the presentation when you get it for your own reference. So hopefully this gives you a good idea of RFID technology. And actually on Monday, I'll talk about an actual example, an actual system that follows the same paradigm from RFID reader, host computer, cloud, and it embodies a whole application. And within the RFID reader part, a new technology development to make it more cost-effective for the application overall. So I'll talk about all that on Monday. Okay? All right. Have a good weekend. Thanks.